Earth?
Oh. Hi, Earth. Bye, Earth. Wait, reverse that. Yeah, it means... Okay, hello everyone, and welcome back to the Entropy Center. So, last time we left off, we just introduced jump pads. Now, so we're going to try to learn a bit more about these, generate some entropy energy through solving entropy puzzles with our entropy brain.
Jumping onto a jump cube from a higher area will spring you further. Just remember to bend your knees when you land.
It's an entropy jump cube, Astra. Use the proper terminology. Okay, so from here, we go boing. Now, what if we jump from here? Boing! Okay, yeah. Test. That makes sense. Also makes sense from a physics perspective. Things that are bouncy will bounce higher when they hit at a higher velocity. It's actually, we use some standard equations for that. It's a simple relationship, typically, that every pair of objects that collide have this one value called a coefficient of restitution, where after the collision, the velocity will always be the same ratio, regardless of what the original velocity is. So let's say coefficient of restitution is 0.5, that is 1/2. If things collide at 2 meters per second, they'll exit at 1/2 times 2 meters per second is 1 meter per second relative to each other. They collide at 10 meters per second, they'll exit at 5. 20, they'll exit at 10. It's the same ratio for everything, for every initial velocity. Although there is a point where that breaks down, and it's the point where the objects break down. If the objects get damaged, then energy is lost to causing that structural damage, and so you won't get as much restitution. But in most cases that doesn't happen. Energy is lost to things like heat and sound, and that's a source of entropy, really. The loss of energy there, it goes into entropy, which is, well, the energy isn't really lost. There's still the energy. It's the free energy that's lost. It goes into the unfree energy, which is entropy. Well, unfree energy isn't exactly entropy. Entropy multiplied by current temperature is unfree energy. Slightly different units. Okay, we've got to put it there. There we go. Now we can jump all the way. Alright. So, okay, we've got another jump here. Alright, simple puzzle. We've got to put it over here first, so we can bring it back and rewind it to be there. Oh, of course, we've definitely got to carry it first before we do all the rewinding. Come on, there we go. Okay, now it's going to have to be in sight from up there, so I think I'll put it in kind of a medium spot and see if I can fall down without as much forward velocity. I'll just walk off and then run once I hit it. There we go, that works. Okay, so now we entropyize it back. Astra, are you following me with the new terminology? This is going to be on the test later. Okay, that should work. And then from here, do a jump to make sure I get all the way, and we are across. So that was pretty easy. And the fact that it's pretty easy probably means we're not generating too much entropy energy. We might need to think of a way to make these puzzles harder for ourselves. Oh, still only... Yeah, see, it's been stuck at 21% charged for a while. These puzzles are definitely too easy. Okay.
This is an Entropy Center emergency announcement. Cataclysmic event on Earth is in progress. All Entropy personnel attend the main deck. Thank Thank you.
Are we close?
My analysis detect that we are one puzzle area away from the main control deck.
Okay, good. Quicker I solve this, quicker we can get there.
Okay. So here, we can get up here with no issue, but the actual puzzle is going to be getting both of the jump pads up here so we can put them on both switches to go through the doors here. And the bigger puzzle is, how do we make this puzzle any harder? Because remember, we're not generating enough entropy energy. We're gonna have to do it with one lobe of our brains tied behind our back. That would make it harder. Might be a bit impractical, and I might need to set up a Patreon to cover medical expenses. Okay. So, first step. The way we've set things up, we just have both... we need to get them both to the middle step, but I think we can solve this by... Yeah, once we've had one up, we can use it to get up, and then rewind it back here. So, rewind this up, and then we just do the same thing with the next step. Which isn't all that hard. I wonder if we can use that effect somehow. Uh-huh. Now that's interesting. Okay. What can we do with this? Oh. Can we catch it? No, I'm trying to move back. Oh, it goes intangible when we're rewinding it. That's disappointing. Hold on, 38.3 seconds? I thought we only had 30 seconds. Interesting. But that should go boing up. And we can grab it there. Okay, there. A little bit of sequence breaking, alternate puzzle solution. Yeah, the thing that I'm trying to think about is why, when we drop one flat on the other... Oh, now they're not both going. So before, they were both bouncing up. That's a very interesting quirk. Okay, here's my guess as to what's going on with the physics here. So, no, I can't use the whiteboard writer here because my mouse also controls the camera, so I can't really draw on screen here, but I'll just try to illustrate it with the cursor. So, what happens when we drop one of these on the others? First, we have one collision with this. So that collision transfers momentum from the falling box to the bottom box, and causes Newton's third law reaction. Remember, there's a little rhyme to that. Imagine you've got a happy cat and you pat the happy cat. The cat pushes back up into your pat. So for every force, there's an equal and opposite force. Or in rhyme form, if you pat a happy cat, the happy cat pats you back. Okay, everyone got the rhyme? So, this is our hand, that is our cat. So, when we pat it, the cat pats us, and that gives force up. And the pads also cause extra force up. This is the cat pressing its back up into our hand. And it really bounces our hand up. If cats don't bounce your hand up when you're patting them, the cat isn't happy enough. You've got to do more to make your cat happy. Now, at the same time, we're pressing down on the cat. So the cat gets pressed down and gets pressed into the floor. So when the cat is pressed into the floor, that's a collision of the cat with the floor, and its very bouncy legs cause an extra bounce from the floor. So it bounces itself off of the floor. Now, does this happen if I just drop that? No. So you have to have the extra force of one on top to trigger that double count cat bounce. Yep, those are very happy cats. Okay, next puzzle time. Sorry, kitties. We have to leave you behind, but at least you have each other.
Warning. A cataclysmic world-ending event is now active. Urgent rewind required. Please enable the Entropy device to activate rewind on Earth.
You know, I probably should be rushing through these rather than talking about cats. What do you think? Sound off in the comments. Would you rather I rush through these puzzles or talk about cats? Or stare at the beverages on display? Would you like some Entropy brand cola? Let's see. Oh, the numbers are worn off. Well, we can count. So let's see. 1, 2, 3, 4, 5, 6, 7. Okay, so number 16. Astro, do you have any change? Crap. Yeah. No Entropy brand cola for us. Alright. Ooh, Entropy Museum. Puzzle areas 10. Apparently, they left out a comma here. Puzzle areas, comma, 10 of them. Cataclysm research. Probably a good idea to research this cataclysm. Can we get over here? No. Okay, no cataclysm research for us. Maybe you can do some cat research instead. Entropy Museum. No, caved in. Oh, it just occurs to me, now that we found that things that were rewinding seem to be intangible, that better explains why they don't want us to shoot the entropy gun at colleagues. Like, if they walk in a room and they come over to you, and then you shoot them with an entropy gun. Now, we know it doesn't affect living organisms, but it will affect their clothes. So their clothes become intangible and go back to the entrance, and you've got a sexual harassment lawsuit on your hands. Yeah, very good advice there. It would be a funnier prank if it dragged the person along with them, but yeah.
Is that Earth?
Oh. Hi, Earth. Bye, Earth.
Astra! What's going on? What happened?
Directive, activate the entropy device.
I'm pressing R2. It's not rewinding Earth. Is there like a big... Okay, big button here.
Active inputs required.
Those cables lead to 2 switches. There must be a way to activate them.
Okay, she's got a big lever. Oh, okay. Why are the switches outside? Oh, Earth isn't doing so well. Is that the end of the cable? That is, or is that a different cable? Okay, your cabling arrangement needs work. I have no idea where the ends are. And it goes up there, over there. Oh, or maybe this is it. It goes over here. Okay, if you wouldn't mind hurrying up, Earth is in the middle of being destroyed. Thankfully, it's being destroyed rather slowly. I think we might have time. We might even be able to just sit here and watch the show, and it'll never complete because the game developers are being kind to us. But that seems like a pretty big risk to take, just to satisfy our curiosity. So, new development, we are not currently on Earth.
Controls are now live.
So, are we on the moon? On some sort of space station? Now, if we were on the moon, yeah, we would be able to jump a lot higher. A space station would require
Entropy device.
some other form of gravity.
Enabling activation sequence. Executing rewind of 5, 4, 3.
Ooh, big entropy gun. Okay, so we are going to prevent the Earth from being destroyed. Oh, or not.
Reactor failure. Cataclysmic event still in progress.
Why isn't it working?
Well, maybe you need to give me harder puzzles.
Entropy energy is required. Directive. Head to the power reactor for maintenance. Complete recommended puzzle areas along the way to charge the Entropy device.
Astra, I don't understand. What's happening to the Earth?
It's exploding.
Stay calm. We can still rewind the cataclysmic event.
Okay, but this just doesn't make any sense, Astra.
It will be okay. You have proven yourself capable.
Okay. Thanks, Astra. Let's keep going.
Yeah, what's happening to Earth is pretty simple. Why it's happening is the big question. So let's go out there, see if we can get a bit of better view, because it does look like the Earth is going to be exploding for a while. I'm getting some glare. But yeah, it is a slightly better view. Get a good picture for the thumbnail of this video. Try a few different angles, don't know what'll end up being best. Okay. Yeah, thanks for posing, Earth. It looks like something like the magma inside Earth is spewing out. I think that's what's going on there. Yeah. Too bad about the glare, though. Yeah, we just gotta get it right behind the tree. Yeah. Oh, there we go. Let's just use the tree for framing. A nice tropical vacation while we watch Earth explode. Huh. There's water here. Or this pseudo-water we've got. So I wonder where we are. Okay, I don't think we're on the moon. Because the gravity wouldn't make sense unless they've got some form of alternate gravity. Or they're messing with our perception of time. But, no, even if they were messing with our perception of time, we would still expect to be able to jump higher. So... get me some massive space station. Yeah, they have to have some form of artificial gravity. And they don't seem to be using centrifugal force to do it, which is kind of the Halo solution of just putting yourself in a ring world that spins around. And the imaginary force you feel outwards takes the place of gravity. Oh, this is one nice gun. So, yeah, they must have some artificial gravity solution. Because otherwise, the only way to get Earth-like gravity would be to go to Venus. And Venus is too far away for Earth to appear that big and has too thick of an atmosphere for us to see it at all. Alright, more puzzles time. Puzzle areas 0 through 4, I'm sure they mean. They aren't just bad at plurals. Yeah, Completed Act 3.
Observation. Puzzle operative looks concerned. Deploying emotional support. Hello, Aria. How are you today? What's your favorite color?
Thanks, Astra. I'm fine. I'm just taking a minute. So, that device can rewind Earth?
Exactly.
Okay. And then what?
Once Earth has been rewound in time, the Entropy Center automatically sends the data to Earth, allowing them to realign their timeline to a more positive outcome.
Right. Well, let's hope so.
Yeah, question. The entropy gun can't rewind
This
level.
is not level 4. This is a wall.
This is a wall.
Hold on. Why are you screaming?
Oh, I was just copying. I thought that's what we were doing. I think I saw an opening a few floors up. Directive. Try rewinding the lift.
Yeah, so I just have one problem. You've said the entropy gun can't rewind living beings. There were a lot of living beings on Earth. I mean, we could maybe rewind Earth, sure, but I don't think... Oh, maybe once they're dead, you can rewind them. That's how it works. So once everybody on Earth is dead, then you can rewind them. Alright. Then we rewind back. There we go. Alright. So the technology is getting even more weird. If it were in office on Earth, you know, I could see them maybe just keeping around the old monitors they have because they still work. Maybe. But if it's a space station, that gets even more implausible they would have this type of technology. So I think they're deliberately going for a schizotech aesthetic, which is just mixing up different periods of technology for aesthetic reasons. Or this is an alternate universe that never invented flat screen monitors, but did invent rewinding time. Okay, I don't know. All I can do in here is get a box. Okay, box, you're going for a ride. Oh, hello. Wave to the robots, everyone. Oh, come on, don't be upset. I want to be your friend. Aww. I'm sure we'll make friends with them sooner or later. Oh, that's a neat effect. They conserve when the elevator rewinds... Oh, so the elevator doesn't become intangible when it rewinds. Maybe it's just the blocks that do that. But yeah, when the elevator rewinds, it's tangible, pushes the block up, then it stops instantly when I stop rewinding, but the block still has momentum, so it pops up. That makes sense. Okay, now I just want to check. I've moved the block around a bit. If I rewind, does it go through me? Okay, so the blocks do seem to become intangible when rewound. Alright.
Where are we?
We are located in puzzle areas 201 on level -4. This is the fastest route to the reactor.
Astra did it too. Does this universe have different pluralization rules? It said puzzle areas 201. Is the weird pluralization actually a clue to the lore or something? This is getting weird. I might be overthinking it. I mean, it is true that the British language does have slightly different pluralization rules to American English, but not these things. Like, one difference is the difference comes in collective nouns, like the team. Like in American English, you would say the team is practicing, and in British English, you would say the team are practicing. That's the extent of the differences. So it's not just being a British thing. Maybe educational standards plummeted after Brexit. Okay. Let's see what we can do. Okay, we can lose control of that. Yeah, it's kind of hard to carry these up. It doesn't let us lift them up by looking up very much. Okay, so... Okay. Well, I'm going to leave it up here just in case I need to rewind, but probably what I need to do is leave that in the center and then jump on it from over here to get across. There we go. Are any power supplies around here? Oh, anything in here? That's interesting. Something over there. Okay, did I miss something? Let's just go in with fresh eyes. Okay, there's a light up here. Yeah. Wait, there we go. It adds back to me. It's pretty convenient that all these power supplies only took a few seconds to decay. Exact same time for each of them, too. You know, now that I see these rocks here, I'm wondering if they burrowed this center out of an existing body. Like, maybe this is the moon, but we're in an alternate universe where the moon is as big as Earth. Or they've invented artificial gravity.
New puzzle element introduced. Springboard. Stand on springboard to launch yourself forwards. Happy jumping.
Okay. Oh, right here. So, how's this work? Can I pick that up? Or is this not the springboard? Is that just... Huh. Okay. Let's look around. Oh, do I need to turn it on first? That's it. Okay. Okay, springboards probably need to be powered on.
Whiplash part of the experience, too?
Ouch! Please fill in an injury report at the end of the exercise if you experience any personal injury. Would you like me to request a cold compress from the medical team?
I don't think there's any medical team alive, Astro. Thanks for looking out for me.
Would you also like me to make an appointment with a doctor about your funny-shaped head?
What? My head is fine. Rude.
Yeah, Aria, so we need to get you some of those leg guards that Shell uses. They prevent her from fall damage and somehow whiplash. Yeah, she doesn't experience any whiplash at all, so it must be the case that those leg guards are preventing her. Don't ask me about the physics. Just trust me, that does make sense. Protecting your legs prevents you from getting whiplash. Okay, we need to put something on that switch. Hello, block. Okay, so what does this switch do? Okay. So that one is on the door, so that's going to be our final state of the puzzle. We'll just have to rewind it back there. We launch ourselves across, put it on there, go through, and then we rewind it back to the other switch. There we go. Break area. Wait, now it's puzzle area 4. Did we cross into a different parallel universe where they use the same pluralization rules as us? I'm honestly getting a bit paranoid about the S's and lack thereof. Okay. Entropy Energy 101. Okay, the last presentation we came across was absolutely horrible. So everyone, place your bets now. Is this presentation going to be... Like, let's put it on a scale of 1 to 5. 1 being as horrible as the previous presentation, 2 being a bad presentation, and up to 5 being mind-blowing. Okay, everyone got your bets placed? My money's going on another 1. So, 1. Yeah, this is a 1. Meet puzzle exercise assistant P. It's about entropy energy. 2. Solve puzzles. 3. Generate entropy energy to charge entropy device. This isn't... yeah. 4. Use entropy energy to rewind Earth and make a better tomorrow. So, this doesn't at all fit with what the title was, but it was marginally better than the last one, because there actually is a through line between the different slides. It's just the presentation doesn't match the title of Entropy Energy 101. So if people came looking for that, they're like figuring out what entropy energy is, they're going to be disappointed. Okay. Entropy Breck. Entropy Coffee. Entropy Loose Notes of Paper. Entropy Phone. Entropy Fan. I honestly wasn't expecting that to work. Okay. Kudos. That actually is an entropy fan.
Did you see that?
See what?
I don't think we're alone.
My rear view camera is quite limited. I do, however, have a great view of your chin.
Seriously, someone's here.
Well, there are all those other little robots. Maybe it's that. Otherwise, I didn't see anything myself. I might have to review the footage, see if I can see it later. The pop-in keeps distracting me. But not much I can do about that without buying a new computer. Okay. So let's see, what do we got here? We've got one jump pad, one launch pad that needs to be activated, and one block. The switch over here looks like, yeah, just one switch to open the door, and one switch to turn on the launch pad. So let's see how far it launches if we get all the way across it. Okay, we do, but we can't get up there. So we're gonna need to take the jump pad across, and the jump pad is going to need to be right there. Okay, that's our final state of the puzzle. So pre-final state, we are going to need to use the jump pad to activate the launch pad without stepping on the launch pad first. Yeah. Okay, there we go. I think I've got it. Then we put this block on this switch and just leave it there. Okay, now we rewind the jump pad back over here. And we can jump up. And up. But wait a second, we're actually going down. We must have used up some charge when we attempted to rewind the Earth. That's unfortunate.
This is an Entropy Center staff announcement. Please may we remind you to never point your handheld entropy device at yourself, others, and, most importantly, other entropy devices. Thank you.
What happens if you do that?
It can overload both devices, sometimes creating a black hole, and then death.
Ah,
Okay, do not cross the streams. Now I really want to cross the streams. I hope this game ends with us crossing the streams. Okay, what do we have? Computer. Entropy HR Department contract reduction. To John, unfortunately your contract reduction request has been declined. As you are aware, there are strict rules and regulations on when Entropy Center employees can return back to Earth. There are specific times where this is simply not possible. Your contract has 10 months remaining. Yeah, that actually does make sense if you're working up in space. It's very hard to get to Earth and back. You have to align the orbits just right so you can make an efficient shuttle. Otherwise, it takes way more energy than you need. It would be exorbitantly expensive. Yeah, it makes sense that there would be big windows. Although a 10-month window would imply we are pretty far out from Earth, like in a separate orbit. But Earth looked very close to us, so yeah, not sure. I think this is just the employer screwing around the employees. Mark Jacobs, family. Hey, John. Thanks for asking for clarification on this. I appreciate for new employees it can perhaps get a bit confusing on how time exactly works here. Oh, something funky's going on with time. That's what I thought. Like, if we are on the moon, maybe time is going more slowly to explain why gravity seems normal. Though and maybe we're just really weak, which is why we can't jump high despite that. When we all came here, we signed an agreement that meant we could potentially never see our families again. But that's okay, we all know this, and that's the unfortunate sacrifice we have to make to the cause. Yeah, capitalism has gotten out of hand. So in your example, if you were to tell your parents you were leaving and may never see them again, then leave and arrive at the Entropy Center for your potentially lifelong stay, what would happen if the Entropy Center rewinds Earth to a point prior to when you told them you were leaving? What would happen if we rewound Earth to a point prior to when you left and when you were perhaps mid-conversation with your parents? Well, interestingly, from their point of view, you would just vanish, without a trace. Of course, we do inform families if this does occur. Remember, the Entropy device only rewinds objects that are on Earth. You remain untouched. Huh. That's an interesting physics. Okay, anything else in there? No. Alright, we've got a jump pad here. Yeah, we can repair that. Now, I don't think we can get up there. That looks too high to jump up. Yeah, even up on the top of the stairs, we can't jump high enough for that. Good. So let's take this with us. See if there's someplace else we can use it. So here, launch over. Yeah, there we go, launch over. And not nearly high enough. Is this a launch pad? It kind of looks like a launch pad, but it's not on and I can't pick it up. Wait, why did that fall? Okay. Go up. Over. And over. Yeah, we're nowhere near close enough. Alright, so what else do we have to work with in here? Now, we could put the jump pad where we land, potentially. Yeah, so maybe this is indicating where we're going to land. Okay, that's collapsed again. We'll deal with that later. So, jump pad there. That'll be our final state. Then we bring it with us to get up here. Rewind that over. Put it there. Rewind that back into one piece. And let's launch. And just without pressing the control stick, see how it launches. Yep, there we go. Brilliant. Okay, where are we now? HR, temporarily closed. Any lore back here? Oh, yes, there is. Okay. Helen Lewis, gambling. Ooh, yeah, rewinding time is probably not a good idea. Not going to be legal when it comes to gambling. Hey Max, I know what you're about to say, but hear me out. I've done it maybe a handful of times now, but no one has figured it out. When I came here, I wrote down all the winning lottery numbers for 2002. Earth was rewound a couple of weeks ago back to 2001. Ah, okay. Okay, we're getting some firmer numbers on time. Although, this is just when this employee wrote it. This could be an old email. But this does imply the time period is closer to 2002. Now, that periodic table and the NFC scanner imply a bit later. So not nailed down yet, but we'll have to see. But anyway, so I emailed my dad those winning numbers, random tip of course, not traceable. Well, I only just found out that my old Gramps won. He used one of them. I didn't think he would, but there you go. So if you remember any winnings from any years, races, lottery, bettings, football, send them to your family. You didn't hear it from me. Yeah, that's definitely not going to be legal. To all Entropy Center employees, may we remind you that external communication to family members is strictly monitored, and there are some situations where it is simply prohibited. We have received some information on potential gambling issues. May we remind you that extorting Entropy technology for personal or monetary gain is illegal, yep, obviously, and will be punished without hesitation. If you know of anyone who may be involved in such acts, please come forward immediately, as this is a serious issue. Okay. I wonder if I've missed many of the intel. It feels like I'm getting through the number of intel pretty slowly, but maybe it's a long game. Maybe there's a lot at the back end. Maybe I'm just missing it. Okay. Alright. We have switch for door. We have time gate with a little ridge. Interesting design. Okay, is there any way to disable the time gate? Well, first, okay, we've got launch pad that takes us across. We've got switch here, and we've got switch for the gate. Okay, those are our elements. And we can go back without going through the gate. So, Launchpad will take us through, but the problem is, if we do that while carrying a cube, the cube will get destroyed. Now, we can put the cube down there, on the switch to open the door and get through, but then we can't take the cube with us. So, it looks like the puzzle to solve here is how do we get the cube to this side of the time gate, because it looks like the two ways across are locked. No, I think I figured it out. So what we want to do is stand on the switch ourselves to disable this while we rewind the cube onto the launch pad. Okay, so now we'll have to figure out a way. Yeah, I think we can pull this off. So I'm just gonna hold the cube up here over the launch pad for a bit. Okay, give it enough time there. Then we put it down there. Okay, we go through. We can't see it from here, but we can start the rewind from over here. And then once we're there, we cancel the rewind. It goes boing.
Oh, God. What did you just say?
I said it goes boing.
Term used for when launching an object at high velocity. Would you like me to remove this word from my vocabulary?
Yes, please do.
Yes.
Boing is the correct
That's
term.
been removed from my dictionary.
And there we go. How are we doing on energy? 17. Ugh. It's crawling back up.
There, do you see that?
I keep missing
I
it.
don't see them. All I see is Jen. So much Jen.
Hey, cut it out. Seriously, look over there.
Hello? Is anyone there?
Fun Entropy Center fact. People used to say that the Entropy Center was haunted by ghosts.
That's ridiculous. You don't get ghosts in space.
Whatever you say.
But come on, Arya, you never heard of Space Ghost? Space Ghost Coast to Coast? Nah. Now, where do I go from here? Because it looks like that's too small for me. Oh, no, it is. I was just lined up. Puzzle 405. Oh, any space ghosts? Sorry for the concussion, Arya. We'll get you some leg guards to protect you against that, I promise. Okay, yeah, so if we're here, we can get that platform over. If something's there, at least. And then this one unlocks a gate at the edge of it. Okay. And we have a jump pad here, which we can move around. So, right now... Okay, yeah, I see it. We got a 3-step solution here. So, final step, we have the jump pad here. So when we're there, we can fall on it, go boing across, and get there. Step n-1, jump pad there, which opens the gate. And step n-2, jump pad there, which brings the platform over, which we get boinged onto. There we go. Okay. And we accelerate. Block over. And go through the door. And final step. Yep, there we go. Oh, elevator. Oh, complete Act 4. This is a wall. Yes, it is. Well, this is an elevator. That was a wall. Okay. Well, I think that is a good place to leave the playthrough now. As I mentioned before, I'll be adding some physics bits to try to explain thermodynamics and entropy onto the ends of these, so anybody interested can stick around, and those who are just here for the gameplay, feel free to check out now, and I will see you all next week. Hello everyone, and welcome back to the whiteboard, brought to you by Microsoft Paint. So, last time I went over the 3,4 laws of thermodynamics, or to go with how the game pluralizes, the 3 law of thermodynamics. In particular, gave you an overview of Law 0, which states simply that there's a property called temperature, which when two systems of different temperature are in contact with each other, the temperature will equalize over time to some intermediate value. That's basically what Law 0 is. Temperature equalizes. But this leads us to the question, what is temperature? Often it is deceptively hard to define things. There are some concepts in physics that are surprisingly hard to define. Energy is probably the best example. It is ridiculously hard to define. Temperature, actually not so much. We can get a good handle at it. But the best way to get a handle at it isn't actually to ask, what is temperature? It's, what does temperature? Or more grammatically, what does temperature do? So we can get an idea of what temperature actually is if we just start listing off things that temperature affects that we can find experimentally. So let's just go through everything we know that temperature can do, starting with what higher temperature can do. So higher temperature will. So, well, let's see. What happens when things get hot? There are the effects on the human body, but those are a bit difficult to generalize. Let's talk about simpler interactions. So one, it will cause solids and liquids to expand. This is how temperature is measured with a thermometer. They've got a liquid inside, which has a known rate of expansion, which is much greater than the solid container that it's in. Mercury is traditionally used, but it can really be done with any liquid. And then they test how big it is at various temperatures and make markings on it to show, okay, it'll rise up through the tube this far if it's expanded as much as it will at a certain temperature. At least these are classical thermometers. Modern thermometers have other ways to do this. Now, gases, they kind of expand. It's a bit more complicated, though. So at constant pressure, cause gases to expand. Or at constant volume, cause gases to increase in pressure. So gases don't have a fixed volume like solids and liquids do. They expand in volume to fill up whatever container they're in. So what's going on here is we can imagine two situations. One is when the gas is in a container that is held to its shape by a certain amount of pressure. And if the gas is heated up, that pressure will not be able to contain the gas as well, and the gas will push at the barriers of the container and expand it. The other is constant volume. So imagine you have something like a soda can where you've just got a gas inside, no liquid. This isn't going to expand because it's held to a constant volume, but if you increase the temperature in it, you will notice that there's more pressure inside. And at a certain point, that pressure will burst the can. Okay, what else can temperature do? Well, it can cause a phase transition. That is, can turn solids into liquids, liquids into gases, or solids into gases. You may only be familiar with the first two of these, like just think about with water, solids into liquids, that'd be ice melting. When temperature increases, ice melts into water. Temperature increases even more, liquid water will evaporate into water vapor. Solids into gases doesn't happen directly with water at normal atmospheric pressure, but there are other substances where this happens. So you may have heard of dry ice. This is solid carbon dioxide. And the reason it's called dry is because it undergoes this type of transition. When you bring it up to room temperature, dry ice will go directly from a solid to a gas. So this type of transition is possible. It just happens to different materials or to some materials at different pressure. But yeah, this is certainly valid. Okay, and what else? Now, one other thing we've noticed with temperature is can enable or speed up certain chemical reactions. And this is kind of the more fundamental thing that's going on with a lot of things that affect the human body from temperature, is because the higher temperature changes how chemical reactions take place within the human body. The human body is optimized to work around a certain internal temperature with exposure to a certain external temperature. Like the human will be most comfortable when the external temperature, let's say it probably got a mostly Americanized, so Fahrenheit, the external temperature is around 70 degrees, internal temperature around 99 degrees Fahrenheit, and similar values in Celsius. Well, not the same values, but convert them. because that's where it's planned for the chemical reactions. Now, the internal temperature has to be kept very close to that. Things go badly if it gets far off. Different parts of the body are best kept at different temperatures. Probably the best example of this, and I'm not going there to be vulgar, it honestly is the best example, is testicles, which have to be kept at a cooler temperature than the rest of the body. This is why they're suspended outside the body, so that they can be kept at a lower temperature with different rates of chemical reactions. It's also why the ball sack can expand or contract, so that it can pull the testicles in closer to the body if it needs to warm them up to keep them at a higher temperature, or expand to get them farther away from the body and let them cool down a bit if it needs the testicles to be at a lower temperature. Yeah, so this all goes into enabling speeding up certain chemical reactions. Now, for each of these points, you can flip all of these to say what lower temperature does. So instead of causing solids and liquids to expand, it causes them to contract. At constant pressure, lower temperature causes gases to contract. At constant volume, it causes gases to decrease in pressure. It can also cause phase transitions, each of these in the opposite direction. Liquids into solids, gases into liquids, or gases into solids. And instead of enabling or speeding up certain chemical reactions, it will disable or slow down these reactions. So that's what temperature does. So putting that together, so we have a good frame for what temperature does. What does it make sense that temperature is? And I think of all of these points, the one that gives us the best insight into what temperature actually is point number 3. So if you think about this, a gas is a bunch of particles in a box. So let me draw this here. All right, we've got a box. We've got lots of little particles inside it. Some of them moving in some direction, some at others, all at different velocity. Now, pressure happens whenever one of these particles hits the side of the box and bounces off. There's a change in momentum of the particle, and if you remember our third law poem, come on, say the rhyme with me. If you pat a happy cat, the happy cat pats you back. So the particle pats the cat, which is the edge of the box, and the box presses back on the particle. So you've got pressure, which is the force over time of all of these particles hitting the edge of the box. So as time goes on, different particles will hit the edge of the box, causing pressure on it. This is the force per unit area is pressure. So if we increase temperature, we know that pressure will go up. So if pressure is going up, this means that one of two, or maybe two of two things are happening. Either we're having these particles hit the side of the box more frequently, or, and possibly, and they're hitting it with more velocity. So it turns out either of these would be explained by the same effect. That is, in order to hit it more frequently, the particles inside, you can't add particles if you're just changing up the temperature. That would change the mass of it, and we don't see that happening. So the only other way that we can increase the frequency is if the particles are moving faster. So just imagine we have one particle that at normal temperature over time bounces slowly from one side to the other. But then we turn up the temperature. If it moves faster, it can hit the other side multiple times in the same time interval. Now also at the same time, if it's going faster, there's going to be more momentum transfer when it comes, since it has more momentum when it hits. So the particles moving faster is going to cause this increase in pressure. So this is probably the best measure of what temperature is. Now, it's the motion of these particles in the gas. Now, it isn't just motion in one direction. Let me clear some space here, because we feel this pressure not just against the top of the box, but against every side of the box. So we'll have some out here, and some out here, and some out here. So that means that we're not just looking at the motion up, we're looking at the motion up, the motion down, the motion left and right. And now, obviously, one particle can't be moving both up and down at the same time. So we have some particles moving up and some moving down. And when temperature increases, we increase both the speed of those moving up and the speed of those moving down. They both go to faster speeds. So a way to express this mathematically, we would call this the velocity dispersion, which is a way to say the typical spread in velocity values. Or if you've taken some stats classes, you could also say this would be the variance or standard deviation in velocity. And this is what's going on in every direction. So you can imagine, like, if we have two particles, one moving up at 1 meter per second, one moving down at 1 meter. If we change it to the one moving up being at 2 meters per second, the one going down at 2 meters per second, the opposite direction, we've increased the variance or standard deviation or velocity dispersion, whatever you call it, and whatever exact measurement you use. So this tells us that from this intuition, temperature is, or is closely related to at least, velocity dispersion of particles in a gas. Okay, so is that it? Well, no. The question is, but what about solids? Yeah, a solid object, so let's say we have this system, rather than being on its own, is right next to another system, which is a solid object. This object is going to have its own temperature, and if we change the temperature of the box that's next to it, like if this temperature goes from low to high, then it will slowly warm this up. But the particles in this solid can't move around freely. So what's going on with the velocity dispersion? Do they move around unfreely? Well, yeah, that's kind of what happens. So let's zoom in on the solid. So if we go in very close to the solid, what it will look like is that we've got, it might have a regular structure that we've got a lot of particles and what's called a crystal formation, forming a regular lattice, it's called. Some solids might have an irregular formation, but these will be connected to each other through some sort of bond, which depends on the solid, but there will be some bond holding them in place. So there are various different types of bonds, and this isn't a chemistry class, this is a physics class. So when you have solids like this, these bonds will hold things in place, but not perfectly in place. So if we look at just the particle in the center, each of these bonds is basically a force. So you can imagine that this is a spring-like force where right at the distance it is, there's no force. But if you pull this particle away, if you pull it down here, then this force up here will pull it back up, and this force down here will push it back up to restore it to place. Similarly, if you go to the side, if you go over to this side, you'll be pushed left by this force and pulled left by this force. Now, that doesn't mean the energy will go away. If you pull it aside, it will start vibrating over time. So what happens if you pull it up and down is that over time, it'll shake back and forth. So you're allowed to have some vibration within the solid without disrupting the whole structure. If it gets too much, it will disrupt the whole structure. It will deform. Maybe it'll disassemble into a liquid where the particles can move freely past each other and around. But in a solid state, you can still have this vibration. And this vibration is kind of similar to the particles moving around in a box. It's particles moving around in their own way. So in a solid, the temperature is still the dispersion of particles. It's just that it's more limited to vibration. Okay. Now, finally, at this point, it took a lot more experimentation to get a perfect understanding of what temperature is at the lowest level. But eventually, we did come up with an atomic explanation for what temperature actually is. So here's what it is. Let me type in black there. Why does it keep switching? Maybe I have to start the box. Okay. So temperature is the mean kinetic energy of random motion. I say random, but it doesn't actually have to be random. It could be ordered, but we'll just say random to distinguish it from the kinetic energy of overall motion. So for instance, the distinction here is, let's say you have a baseball and you throw the baseball. There's going to be an overall motion of that in the direction you throw it. But the random motion we're looking at is just the motion relative to the overall motion. So you would like subtract off the motion of the baseball. So one other way to say that, if you want to be technical, is peculiar motion, which is motion peculiar or distinct from the overall motion. And then this is the tricky part. I'll explain it in a bit, at least a little bit. By 1/2 the degrees of freedom and the Boltzmann constant. Okay. So let's go over these bits. We've already talked about why it's the kinetic energy. The Boltzmann constant is also pretty simple, actually. This is just a way of changing units. That's really all you need to think about it, because kinetic energy has units of joules or kilogram meters per second squared. Temperature has units like Celsius, Fahrenheit, Kelvin. Particularly when we're translating it this way, we have to go with something like Kelvin, where 0 is absolute 0. So the Boltzmann constant has units of, I should type that out rather than putting it. So units of Kelvin divided by energy, which would be joules, where joule is kilogram meters per second squared. And then this is just a unit conversion. It converts kinetic energy into temperature. The Boltzmann constant is used in other purposes as well. We'll see it again when we talk about entropy. Then that's why the 1/2 shows up. If we weren't using the Boltzmann constant for other purposes, we would just absorb the 1/2 into the constant, but we do, so we have a factor of 1/2 here. So the 1/2, you can just say that's a constant that comes out of math and not worry about it. The final bit is, what are degrees of freedom? Well, degrees of freedom are basically how many different ways something can move. So imagine you've got like a particle in a box that can move translationally, just shifting where it is, in 3 dimensions. And it can also spin in 3 different ways. Now, what about a particle that's part of a solid? That can vibrate in 3 dimensions, but it can't spin. The spin is pretty much locked in place. Now, maybe you can get some spinning back and forth, but let's just say, for sake of argument, that it can only vibrate in 3 dimensions. So, in the first case, we've got 6 degrees of freedom, and in the second case, we've only got 3. So this means that if these 2 cases have the same kinetic energy, like let's say they have a kinetic energy of 1 joule for each particle, the top case, you would multiply it by 6, then by half the Boltzmann constant, and the second case, you would be multiplying it by 3. So, in the top case, the particle in the box would have a higher temperature despite having more kinetic energy. Despite having the same kinetic energy, it would have more temperature. And this is something that really had to be experimentally confirmed. You have to test things out very carefully to see this. It isn't really intuitive why it works this way. The way temperature moves from one thing to another is too complicated to model, but this has been well tested and shown that the relationship does work this way. So putting it all together, this is our definition of temperature. So we've talked about what temperature is and what it does. And what it is, all you really have to remember is temperature is typical kinetic energy, and if you really care, remember, use the degrees of freedom, so different things can have a slightly different relationship between kinetic energy and temperature, and then to convert units, you use the Boltzmann constant. All right, so I think that's a thorough enough dive into what temperature is. Next time, we'll come back and we'll talk about the first law of thermodynamics, which is basically conservation of energy. But we'll get a bit more into it then. So until then, thank you everyone for watching this far, and I will see you next week. Bye-bye. Thank you very much for watching, everyone. If you enjoyed this video, please leave a like, subscribe, and click the bell to be sure you get notifications of new uploads. See you again soon.